You have to do it, yeah, a couple times, right? Twice? But is twice so hard?
Hi, Joyce. Yes.
Okay, then let's make it even more fun. Now what?
Oh, no. Oh.
They make it better or worse? What? Why? Exactly. Now, could you do it 5 times or 4 times? Yeah. What would you want to? No, but you could. 4 lucky 7s, right?
Wait, 4 lucky 7s in a row? That's a jackpot. I'm going to Vegas, Miss D.
You are? After this one?
I'm taking this integral and I'm going to Vegas.
So we'd have 1 u du, or 1 u be x to the 4th, and get a cubic, right? Another u would be the cubic to be a quadratic. Another u would be the quadratic to be the single. And another u would make it then constant, and then we'd be good to go, right?
Someone.
Okay. Here's the idea. Tabular method. Some people use this method in some ways for everything. I think it's kind of confusing if it's for one of the normal ones, hence why I showed you lucky number 7, or lucky 7. Okay? But technically you could use this all the time, and here's how it goes. Ready? You just make a table, and you put the u on this side, and you put the dv on this side. Make a table. You're going to put the u's on the left, and you're going to put the dv's on the right. Okay? What would be my initial u? X to the 4th, right? What would be my initial dv? Sine of 4x dx. Now technically this is a shortcut, so we're not going to show all the notation, but the dx does allow you to integrate, etc., etc. On the u column, you're deriving down, and on the dv column, what are you doing as you progress?
Integrate.
Integrate. So over here to the left, I could say, okay, my first u would be 4x cubed, right? Or I should say my du would be 4x cubed, which would be my new u of the next step, right?
Yes.
And then, and then as we go on, then we have 12x squared, right? Then we have 24x. Then we have 24. Then what?
0.
True. What's going on the other side?
Sine, cosine.
1/4.
Sine, cosine, negative cosine.
1/4 cosine 4x. Then we have negative 1/16.
No, it's negative cosine.
Ah.
Negative cosine.
I
Integral
thought you
sine.
were going to say negative on the next step, so I was copying. There we go. Negative 1/4 cosine of 4x, and then negative 1/16 sine of 4x, and then
Positive 1.
64th cosine of 4x, and then positive
128.
128, right? 128. Okay. Sine of 4x. And if we were to keep going, it would be negative 1 over
256.
256. Good.
I memorized that because over the summer I learned binary.
Mm-hmm.
So it's a
Computer program that would do that. How does tic-tac-toe work? Will you guys tell me?
tic-tac-toe 3 in a row, possibly.
No. Hasn't been up to 3.
The book had like arrows and multiplying by 4.
Okay. Can we just think of the formula for a second?
That's going to be a long zigzag.
Basically. Why? Because when you have, or when you choose the integral of u dv, question, what does that equal? uv minus v du, right? So uv,
Raise.
there's the u, and we need to get to the v by skipping down 1, right? Because we have dv, and then we integrate and we get v.
Right.
Okay, now on the next one, who's going to be the next u?
Oh. Ah.
And who's going to make your next v?
That one.
You go until you can't go anymore, because 0 times anybody will be 0, and guess what you have? Now wait. The first is just uv, right? So he's going to be times a positive. He's not necessarily a positive, but he's times a positive. Because he's just normal UV. But from there on out, you have UV minus an integral. So then, that sign's going to be flipped. But that's going to be double flipped, so it's back to a positive, then flipped again, and then double flipped, and then we're good. So what does that mean? The final answer, without having to do integration by parts over and over and over and over again, is going to end up being UV, so minus 1/4 x to the 4th cosine 4x. Negative, because there's a negative times a positive is still a negative. A negative times a, is that next one negative? I just covered it. A negative times a negative is a positive, so 4/16 will be 1/4.
Why is it positive in the first one?
Wait a second. It's not positive, it's negative. See? Negative.
Yeah, you go positive.
4/16, give me a second. 4/16 is 1/4 x cubed. Sine 4x. The next one times a positive 12/64. Can that reduce? A little bit. 3/32. The next one would be minus
Would it be 3/32 again because it's the same, just times 2.
24/128. Should be. You could think of it as 6/64, but that would reduce again, right? So 3/32. And that's a minus because a negative times a positive is a negative. X sine of 4x. And then we have a minus. A positive times a negative is a negative. 24/256. One stays the same, the other doubles. That'd be 3/64, right? And what can we not forget? Because he's an integral. Plus. And you're like, wait a minute, what? I need to get the tic-tac-toe. Basically, this would be a tic-tac-tac-tac. Whatever, toe. He just used tic-tac-toe in the example because it only had 3 connections. This one ended up having 1, 2, 3, 4, 5 connections.
I don't get it. How do you get the fact that the first one's positive?
Because when you take the integral of u dv, it equals a positive uv minus another integral, which is going to be minus the next uv. Then you're going to have minus a minus, the next uv, and then minus minus a minus, the next uv, and then minus 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 minus.
But it was a negative 116.
Are you talking about the first one because there's no 16, or are you talking about the second one?
Well, I commented on the second one, but the first one, I don't know if it's negative.
It'd be
positive.
uv,
Right.
there's no sign in front. So when you take the integral for integration by parts, the integral of u dv is equal to uv. There's no sign in front.
Right.
But then for the next step, there's a minus of the integral of the new v du.
Right.
Right? So then when I integrate this one, I'm going to have a new u with a new v, but there's going to be a minus in front. So it's minus whatever that one is. But then as you do it again, you're going to have a minus, and then inside there's a uv that has the negative, and then there's going to be another negative. A negative negative makes a positive. Basically, the sign's alternate.
Right.
And that sign is being multiplied. Well, you still have uv, but there's no additional sign in front. So we say multiply the u and v, multiply by a positive. But for the next one, you're going to have another uv, but you're going to need to multiply by a negative. The next one, you're going to have another uv multiplied by a positive because it'll be 2 negatives, and then et cetera, et cetera, et cetera. Long story short, the tabular method, the signs alternate in the sense of not what the answer necessarily is, but in the sense of you take the u times the v and then you multiply by alternating sign, starting with positive, because the integral of u dv is equal to, in a sense, positive 1 times uv.
So if that was a positive 1/4 cosine 4x, it would be positive, and then x will still be negative.
A negative times a positive is a negative. If it was a positive times a positive, it would be a positive, just like the rules say.
So it's always plus minus plus minus plus minus.
Times positive times negative times positive.
Um,
Because this one technically is minus plus plus minus minus plus.
so it's times plus times minus times minus. Multiply plus times
U,
value.
u times v times a positive.
Got
U times v times a negative. U times v times a positive.
Now I understand.
Yeah?
Yeah, I just write it down.
So, a couple more seconds. So similar to the loopy example yesterday, there might be a trick to solving, but remember, we still have to not forget our plus c at the end, okay? We have to not forget our plus c at the end or else we'll be in some trouble because we are solving an indefinite integral, but it doesn't naturally occur in the sense of if we get too stuck on the method, we might forget what's going on exactly. Does that make sense?
Yeah.
So what if I was to ask you to use, oh, I don't want to do that quite yet. What if I was to ask you to use the tabular method? To solve with integration by parts of the following. I don't really need that, that's it. Let's do it anymore. What do you guys think? Yeah, same instruction. But thank you.
Yeah.
Depends on how you choose it.
You can integrate over. But then the one half x squared, or that x squared gets more complicated. It's still working though.
So then you have 1 over
Or
x.
you can do integration by parts
Divided
divided.
again, 1 over x squared, divided again, and then eventually they'll match up 1, right? Right.
Or maybe you can simplify.
They're going to cancel out eventually.
This one's an example where some would not necessarily use the tabular method, but some that solely use the tabular method would still be able to solve this. It just wouldn't be necessarily a repeated application. So I'm showing you an example of using the tabular method for a non-repeated application. So just because for the repeated application we say go all the way until it hits 0, well, maybe this example you don't need to go up. What do we have to choose to be here? You guys already figured that out. We have to choose ln, Liate, right? We have to choose the logarithm. So therefore if we have our, this isn't necessarily one that I would use the tabular method for, but I have seen college professors with kids that have tutored or alumni that have come back and asked. Who have them use the tabular method for every integral. So I'm just trying to show you how the tabular method works when it could keep going on forever. Right? What's the du? If you keep on going pretty far, you're like, stink, I'm going to keep on writing forever. Okay, well maybe not all uses of the tabular method necessarily have to go to 0. If I was to do v, if I was to integrate, what would you get?
1/3 x cubed.
Okay.
So again, negative 1 over x squared. For the u.
If I, oh, yeah. I see. Sorry, we're gonna-
And then 12 x cubed for.
Now, hold on. 'Cause about this point, you should, and some of you would realize it earlier, like, forever.
And
Okay.
then x squared, I think you have it attached.
We can. Wouldn't our tabular method say, what color did I use in last week? Blue?
Yeah.
Okay. That would be a positive, right? That would be a negative. Why am I not going to go any further?
Because you don't need to, because we have
X
x
on the
cubed.
bottom cancels out.
X on the bottom is going to cancel.
We don't go up x.
So, hold on. Ready? We would get the integral of dv, right? Is equal to uv, which would be 1/3 x cubed ln of x minus, technically, what is this telling me? It's minus the integral of 1 over x times 1 over 12 x to the 4th, which I could pull out the 1 over 12, so I'd have the integral of x cubed dx. Those people that kind of teach the tabular method for every integral, they're not just using it when the u can go to 0 and then you can do repeated integration by parts over and over again. They show just how to do, hey, uv minus the integral of v du, and then they would write it. And they're like, okay, let's go. They're technically doing what we're doing with Lucky 7, they're just showing it a different way. But at this point, you don't really need to go any further because whatever, we're ready to go, right? So you just go ahead and say sweet. So we have 1 over 12 times the integral of x to the 3rd is 1/4 x to the 4th. Oh, I wrote it.
No. Because there's an x on the bottom.
Oh, yeah, I did x to the 4th over. Thank you.
Oh. Oh.
I was only looking here, not there. Awesome. So anyway, some people do teach the tabular method as in that's the way to write it. And they teach, instead of Lucky 7, they say uv minus v du, and then it's, you rewrite it, and then if that doesn't work, or if you get used to looking and multiplying and saying, but I can't integrate that, all right, go again, can you integrate that? Nope, and you just keep on going. But I think Lucky 7 is a little bit easier to see than the tabular method for one that doesn't necessarily need repeated applications. At this point, kiddos, be amazing and AP-ish. How could they simplify?
Pull out 1/3.
No.
48.
Well, that's 3. No.
Not a 3, not a 1/3, but definitely a 1/48. Remember, they let those fractions be totally out. But how would you pull out a 1/48 from 1/3? Do you remember?
You got 48 or 48.
16.
12.
Yeah, 16.
Right.
16.
You have 16. I pull up x squared, ln of x. Minus, I already pulled up the 1/48. I pulled out x squared, so minus x squared. Just because I don't know those fractions are sometimes really hard to see.
How did the
Oh, I totally wrote it. So there should be an x left, yeah. Oh, I didn't pull that next to you. So 16 is fine, and that would just be a single x, and that would be x. Good catch. So tabular method makes sense. I mean, this is the best application, I would say, right? Like, we don't want to do repeated Lucky 7 over and over and over. That's super annoying, true?
True.
So the best application is when it's repeated, you see, you're like, oh, that's a 4th degree, 5th degree, 3rd degree, even a 2nd degree. And there is no logarithm, right? So we would choose the algebraic on the last one. There was no log, I should say. Let's go look at it. Too far. There is no log in a trig, so therefore we take the algebraic or the polynomial piece. And it's like, hey, the tabular method makes life a lot easier, a lot quicker, a lot simpler. But over on this one, some people do it. I don't personally like it, but I just wanted to let you see you could use tabular for any set or any application of integration by parts. I just don't like it.
You're right. Like you said, it's cool.
Right? I think it's better. I don't know. It's clearer anyway. You guys don't necessarily need to write this down, but I think probably you figured out this quick little summary of, hey, what should you think? For instance, if we see x to a power times any exponential logarithmic, unless it's something that maybe I could do with u sub, who's always going to be the u? The x to the n part, right? And if n is greater than, well, 1, if it's 2 or 3, you're probably using the tabular method just to make life easy. When you have any sort of algebraic piece with inverse trig or the logarithm, you're not choosing u to be the x, right? So the power you're choosing u to be the ln or the arc sines or the any other arc trig or inverse trig, because then that first du gets rid of the logarithm or gets rid of the inverse trig, and suddenly it's all algebraic, and maybe you can just solve from there. And then last but not least, if you have two that cycle, meaning you're going to keep on going forever, what do you have to think?
Set it equal to the original and stuff.
Keep that original in the equals as you go until you can match up two integrals, get combined like terms. It's the loopy one. You keep going until it loops around, and then you can subtract it or add it to one side, multiply the coefficient over it, something like that.
So the bottom one, couldn't you just be like, tabular method?
Technically, but you have to be able to see when you get it back to the beginning. You still have to write it all out, I'm pretty sure, and then move it over.
Yeah.
So you could use tabular if there is a repeated application, and usually it's two. Usually two is enough, right? Because sine goes to cosine, cosine goes to sine. There we go.
I forgot tabular for upgrade.
Just be super careful when you're doing the loopy example. Watch out for signs. Did anybody do loopy last night? Yeah. Where are you going to make mistakes? Signs and coefficients, right? Because you have to keep those parentheses in there. Don't be killing any seals. Make sure you're distributing. That's where it gets tricky.
That's just funny. I did it and I was like, wait, that's supposed to be a plus. Or minus.
Yeah.
Like I wrote plus and then I erased it right afterwards and wrote minus.
You guys ready to check the evens for the most part?
No.
Okay.
Just up to number 20.
Okay.
Yeah.
Let's go ahead and get out. We'll check some of them. We'll check the rest later. Because, yeah, you guys didn't get the tabular, right? There we go.
Oh yeah.
You can just put it in your tray if you want.
Inside the tray or inside the folder?
On top.
Can I get a stamp?
Right this second? No.
I don't like the arc or the inverse one.
How far did you get on one? Oh my god.
Basically, it's a bad.
7.3, right? Okay, I was off on that. I don't know why.
God, did you get a book for the tabular method?
No, I skipped it. I just didn't have
You didn't?
all we do.
She was multi-purposing. Multitasking? Multitasking. That's why Amanda Johnson can accomplish what Amanda Johnson can. What evens? 2? Sorry, Joyce, I just hit the microphone. Okay. Number 2. X times e to the x minus e to the x plus c.
What's the business on the left side?
Oh, E, X.
Oh, they're just showing the uv minus the integral of v du.
Yes, got it right.
Does that make sense?
I figured out the E to the X. That cool.
Sure. You do you. Remember next one.
8.
1/2 e to the 2x plus c.
What?
I do the wrong one.
Oh, hold on. Wait. You check. Is it the wrong one?
Yeah. No, wait, is it?
No.
You sure?
It's number 8.
What page was homework on? Who has it right there?
Yeah.
354.
What? Oh, 350. Oh, 8.
Oh.
Yes, T squared.
Wait, what's going on? Hold on. Maybe it probably gave me the 8 from up above. Hold on. There we go. Sorry. I forget that it sometimes doesn't go the way that I would go. Number 8, 1/3 t cubed ln t minus t cubed over 9 plus c. I would have pulled out, what, a 1/9?
Yeah.
Yeah. So that would have been 3t cubed ln t minus t cubed. Pull out the t cubed too.
I just did a. I simplified it somehow to.
20.
20. Loopy. Oh no.
Get behind.
Adobe is in Calc 4.
Thanks, buddy. Go team. Give me a sec. I know. Thank you, Georgie.
Maybe you should have done it with a British accent.
Well, maybe the Lord allowed. And that is okay with me. Or at least it should be. Or it needs to be. 7-3. Exercises. There we go. And we're going to number 20. Got it. Boop, boop. Negative 1/5 e to the negative x 2 cosine 2x plus sine 2x.
What? I didn't get that. I got e to the negative x times sine 2x minus e to the negative x times cosine 2x all over 5. Let's see.
That's okay, except there should have been a negative next to your sine one.
Really?
Mm-hmm. Or no, next to your cosine one.
I'm dumb. I factored out a negative
Oh, and then you
It
didn't
said sine
see.
2x plus.
Okay,
I
there you
don't
go.
know, that was weird. It looked like an erased plus, but it was
Yeah.
an actual plus.
Alright, you guys set up to number 20, right?
Yeah.
Boop. Alright. Ready? Back your spirals.
Oh. Oh, okay, this page is just moving. Oh god, so good. Holy crap.
Is this out of focus today?
I think we could use the middle wheel. No, this is not a problem.
Doesn't seem about right, doesn't it? No. I think it's got fudge, not many people are. Oh, wait.
Ooh,
Yeah,
that's way
That's
better.
better, right?
Mhm.
How did that happen?
my eyesight was blurry this morning. I thought it was just early morning and sleepy.
I was starting to get afraid of that.
Eyesight's failing.
Well, when this was blurry, then the overhead this morning was blurry, and then I was like,
Oh, we use the overhead? Or
Oh, baby. For a card match game.
You do not wish you could do that one. Trust me.
No.
You didn't even know it's hard, Miss D.
well, in that case, I
There's
would
only
just.
one first derivative.
In that case, I just want to use the
What about the
overhead.
one where it's like there's like numbers, then Roman numerals, then letters, and then capital letters, and then
it's that one.
is that one? Oh, that's the worst one.
There's the one with blue and green, then there's the one with red and green and yellow. And it's like Christmas colors, red, green, yellow, for the sky. Oh, you guys already stuck? You're pondering.
I'm pondering.
I'm trying to see if I can figure it out. We're not ready.
I agree
What,
with
holy
Joy.
shower?
Oh, -12%.
Wow.
What?
Can't do that. 6 times 3 is not 9. Okay, my 5 minus 1 wasn't 5 either. Oh, that's
What darkness here. Oh yeah, right. This I made a stupid mistake. I mean really dumb.
Wait, the answer was C.
Which one?
My graphing calculator lied.
On 13? You used
Yeah.
your calculator for 13?
I checked my work, and then it said it was wrong. So it said it was 1, and I was like, ooh, I put 1.
Oh, really?
And then I tried, and I got my work to make 1.
You put one, maybe your parentheses were off with your
Yeah,
1
that's
over
okay.
cosine squared.
Must have been off.
Well, that's pretty cool. You should
So
test yourself
I
more
had my answer right. Like, literally, I had my answer right, and then
Did you change your work? 'Cause I didn't remember your work not matching up.
wait, well, look, at the end. So
They give you half
I
credit
had pi
on
over 4 times 1, or 4 over pi times 1. And I plugged in my calculator and said the answer was 1. But I had 4 over pi times.
I know, I was
0.
really confused. And
And then I was
I
like-
don't get it.
And then my calculator said
Then
1,
you
so I
got
was
me
like, oh,
against
I
one.
must have messed up with my trig, so I was like, pi over 4.
But it was average weight.
1. And I had it right, and it's stupid, and
Oh,
that's it.
No, you're smarter than your calculator, and I'm proud of you. You just need to trust
I
yourself.
want to forget the
My test begs to differ.
Depends, that problem kind of proves it.
Oh, I heard something
And I
break.
forgot abs.
You done?
Ooh.
Do I just double check you got it right? I was distracted when I did that.
Misty, did you finish the key yesterday?
The problem was when I did some of the problems, I was distracted, and when I'm distracted, math doesn't always work out super well. So I would have checked it while I was distracted, and that's fine now. Well, either.
So number 2 is Sam checking. Say.
The substitution of new x on y is made.
Holy wow. Okay.
You're just asking us to integrate?
It'd be square root of Sine of
It's
y.
asking you not to integrate, but to try the substitution. It's actually called trigonometric substitution.
Oh.
It's something that we don't really
You
need to
get
do
sine
with
squared
DC.
y
Yes,
over.
because
Do you see?
the property on the bottom. I was trying to figure out how they got rid of the 1 minus, the square root of 1 minus
And
that.
cosine. So is it?
Oh, you can do that.
You can't.
So the 1 square root minus x
Wait. What
Integration
minus
on crack, can you square?
sine squared,
Mhm.
and
Sine
then
squared
add
is
the
x.
sine squared is x.
So then plug in 1 minus sine squared,
So
which
we
is
just-
cosine squared.
And
Square
then-
rooted is.
one.
Whoa, you just lost me.
Yeah, sure.
It's d, but it's a. Oh.
Hold on, do you get one for e?
I got the sine squared over cosine, but I think I did it
Yeah.
different than what you did.
Yeah.
I
Maybe
might have messed up on that.
you can got it.
Because I have, if you have,
Because then this would be sine y all over square root of 1 minus sine squared of y, right?
is it root x equal to sine y?
Uh-huh.
So,
So that just substitutes, but then for this one, it's underneath, so I just need to get x alone, so I square both sides,
okay, I see what you're
and then I plug in.
okay.
And then 1 minus sine squared is cosine squared. And cosine squared square rooted is
But that's not an answer.
uh-oh, hopefully the bounds match.
But you said you have sine squared over.
Oh, sorry,
There you go.
sine. Sorry, sine.
No, but it shouldn't be squared.
Oh,
Because if you have x equals. Yeah, that's what.
so we have sine all over cosine squared.
Oh, wait. How did you know that the square root of 1 minus sine? Oh, it's like it's a Pythagorean, right?
Mm-hmm.
Yeah.
I think
Well, that doesn't match.
this D, I think it would be.
Oh,
you have
secant.
root x, so then you square sine, and then you have to add 1 and then divide by a negative. Or subtract 1, divide by a negative, so you have negative cosine squared, or negative sine squared minus 1, which would be sine squared minus. No,
Just guess.
But dx should not be equal to dy. You have to find the y.
Wait a minute, there's a 2 on the outside of p.
Yeah, that's probably just the even property, and we haven't dealt with our bounds yet. So hold on. What were we being careful of? Not being careful of.
Oh, we didn't.
What did I illegally do?
You switched the ds. I was wondering about that. I was like, oh, she probably just.
So then Jackie was like, oh, wait a minute, but we need to get dx is not dy, we can't just substitute. So we have to find dy. Uh-huh.
So that's why we have cosines. No, never mind.
Well, we could derive either one technically,
Oh, well, we have sine
Y equals sine inverse of square root of x.
cosine.
because I could do 1 over 2 square root of x.
I had to get that.
No, just derive
Yes.
sine squared.
Yeah, you could do it. I just started going for it, sorry. Cosine y dy, right? So then dx is equal to 2 square root of x, which would be 2 sine y. Cosine y, right, George? So it turns out to be the same. I'm writing all of my slip in. So we plug and chug, Uh-oh. Was one of my eliminated ones actually right? Yes. Why? When I go to plug in,
Squared over.
yeah, and I have 2 on the outside, sine squared y. The cosine cancels. Oh,
This
snap.
2 sine.
So it's
What?
d.
How do you get 2 sine 1 cosine 1?
I multiplied up 2 root x, and who is root x? Sine y. Or you could have taken the derivative here, and dx is equal to 2 sine y cosine y dy. Either way.
So this e.
So then the cosines cancel, the dy stays,
Go to our
the sine
bounds.
times sine squared, and then the 2, and the bound we haven't even really dealt with.
So you.
So all we know so far is that's not the right answer. That's not. And then the bounds, yeah, who's my
A is not, and D is not the right answer because they don't have the 2 on the outside.
Because I need y bounds, right?
Right, but A and D can't be right because they don't have the 2 on the outside.
Yeah, hopefully there's not the weird.
Oh, unless you're right, unless it's like a half.
But there shouldn't be, right? Because we're doing bounds, not inside the
Yeah.
integral. So then if I go ahead and plug and chug what? Plug and chug 0
For x.
for x, square root of 0 be 0, sine of who is 0?
So pi over 4. No,
0.
pi over. It's pi over 2.
Square root of pi over 2.
And square root of 1 over 2 is root 2 over 2, which will be at pi over 4. So
Oh.
my final answer should be, right? This is root of 1 over 2 is 1 over root 2, which is root 2 over 2, which is the 4.
Is that because you divide it by 2? Or is that the only way it works?
You plugged in 1/2.
I plugged in, same way I plugged in 0, and that happens when y is 0. I plugged in 1/2, and root 1/2 is root 2 over 2, which happens at pi. So I'm plugging in my 2 bounds to x's, because these are x bounds right now, right? Plugging in for x, solving for y to get my y.
Is that like u of a and u of b? Or is it something else?
But I need, I'm not solving for u, I'm solving for y. Because that's my new variable, and then these are x's. I'm just plugging into the x's, solving for the other one. So the problem is u's not isolated, which is what makes it a little bit tricky. Did you guys already agree on number 1? Sorry, I got distracted. Yeah, E. Okay, we'll see.
It's because it's
I didn't
the,
check it.
it's because the only way for y to be positive when it's negative, it's an e. Everywhere else it's gonna be negative when it's negative.
In the first quadrant, in the second quadrant, y's are positive, negative.
I just looked on
Third
the
quadrant,
y-axis.
Yeah.
Because then x doesn't matter, you
Yeah.
only look at the y's.
Because x is equal to 0, so we can ignore all the x's.
What about the third quadrant?
Well, it doesn't really matter because the only way for the y-axis to be true is if it's e.
Y-axis?
Oh, because the y is being cut into thirds. So then when you have a negative times a negative, there will be a positive that's cut into thirds. So when you have a low y, you have to have it 3 times down to make it go positive. So if you have like a -5, -5, the x -5 is going to be stronger than the -5 being cut into thirds. Does that make sense? Are you down to number 3?
Oh.
But we know him, right? Because all we have to do is integration by parts.
Those are rich.
If it was an x squared, it would be just u sub. If it was an x squared, it would just be u sub. Because then u could be x squared, du could be 2x, and it wouldn't even have to be integration by parts. But since u is 2x, du is 2, that doesn't match. So it's not going to help match.
Half.
Alright, so I'm gonna write it like that. Yeah. 1/2 e to 2x, right?
Yeah.
So 1/2. So x e to 2x over 2.
Minus. Yes,
And then minus 1/2 e to the 2x,
So that it's.
which is going to be minus, so not that one.
Wait,
So it's.
that is.
No, it's it's a.
Let's see. Wait,
This doesn't have to
okay,
be a
then
negative.
minus, yeah.
And the integral of 1/2 e to the 2x would be 1/4, right?
Yeah. Because the half something else.
And let's see, we should end up with. Look at you guys, a whole new problem you can solve on 18 months. Does that make sense?
Perfect sense, actually.
Let's just leave the FRQ for now. Sound good?
Yeah.
Oh man, are we dying today?
Well, I got a lot of sleep last night and I didn't even catch up.
Did you guys have any things? I understand. That was me last weekend. But I'm older, I'm allowed to do that. Homework help.
Yes.
Really?
Number.
I don't think I've ever had one of these.
Number.
I don't think I've ever had one of these.
You didn't do that.
31.
31. Alright, we'll do one homework help and then we'll peek at what the next section is and then you guys just finish homework 7-2 for tomorrow. Sound good?
Sounds great.
7-3.
I only have one request. Can I just send this in the picture?
Okay, what's the example?
It is dy theta equals theta
Polar.
secant -1 theta. I mean that I meant
Wait.
What did you mean?
arc
Very
secant.
nice.
That's what I meant.
Oh, same thing though, right?
Yeah.
Secant inverse?
And then
Yeah, I agree.
theta is
Oh.
greater than 1.
Thank you. Gerardo caught me yesterday. That's how it was. Theta is what?
Greater than 1.
Or equal to? Just greater than. We're solving a differential equation?
Yeah.
Okay. Very first step,
Equal to 1, it would be undefined.
Yeah, you're right. Okay, so we have to separate the variables, right? You're right. I don't think we did inverse trading class at all yesterday, did we? It's in here. Cool. Now what? Yay! We got one. Now what?
So we have theta.
Yeah,
is
who's you?
u,
Good.
UV is secant inverse. Can we calculate that? So
Beyonce. If we have inverse trig and there's no logarithm, guess who's being u? Right? A little different than we're used to. True? That's why inverse trig comes before algebraic. Because, why? When you take the integral, no,
derive it.
thank you. When you derive secant inverse, what do you get?
1 over
absolute value.
Oh.
It's the problem, which is just like
Why does that sound so simple?
because do you see this right now?
I mean, now I do, but.
And then we have
Is that
to
okay?
integrate that.
Wait, isn't that like arc sine or something? Move on? The du?
No, that's secant inverse.
Yeah, I totally forgot all of them after that quiz.
You should remember that.
I remember them for the quiz and then totally forgot them afterwards. It's embarrassing.
So UV, right? Integral of du.
You cancel one of the things.
Is there any sort of restriction on theta?
Theta can I
Can
equal
equal
1
1.
or negative 1?
It has to be greater than 1.
Why is that a big thing?
I don't know.
Because it has the value
Because it's always going to be
Bing.
positive.
positive.
Always has
Ooh,
to be.
ooh, ooh. So what can we do with the theta?
You theta over theta, or theta over root theta squared minus 1.
Ooh! Do we need integration by parts? Do we need inverse trig or just plain old U sub? U sub!
U equals root theta squared minus 1.
Ah, don't make it that hard.
Theta squared minus
Yeah. Theta squared minus 1.
2 equals 2 theta.
2 theta d theta divided by 2 theta.
What do you say?
I don't know.
Is it in
Or
Russian?
was saying
Is it bad Russian accent? Hey George,
It's a nothing.
I dare you to try New Zealand instead of
You have
Australian
any
accent.
bleach?
No,
I legitimately, would honestly expect you to have bleach.
So I have the integral of
Drinking hand sanitizer do the same effect.
You'd actually survive that painfully.
focus. So we go ahead and we have the 1/2 already. When we plug in, we have u to the negative 1/2, right?
Did you forget one?
Ah, I haven't put them in yet. Good call. And then we have the theta over the theta cancel. We have another 1/2 come and join, so that'll be 1/4. And then we have our du, right? We end up with y equals 1/2 theta squared secant inverse of theta minus 1/4 times u to the positive 1/2 times 2.
I'll just put it.
So y equals 1/2 theta squared secant inverse of theta minus 1/2 u to the 1/2 of u was
You is very delicious.
theta squared minus
For delicious.
dun dun dun.
And then,
That cool?
yeah.
Man, just helped you out. For those that didn't get further. Okay, wait, pause. What on earth is coming next? Woo! Growth and decay and separable differential equations. Psh, we got this. Alright, cool kids, I'll see you tomorrow. Finish up 7.
Joyce, if you like this video, like, subscribe, leave a comment, description below.
Christine, what if the problem set evaluates the interval by using